Okay, today we're going to start looking at solubility curves. And what a solubility curve does is it shows us how temperature affects the solubility of different substances in a certain amount of water. So on the screen right now what we have is two common substances that we're familiar with, sugar and salt. And we can see that temperature has an effect on the solubility. You can see the curves are changing, especially with sugar. And what this shows us is, especially with sugar, is that as temperature rises, you're able to dissolve more and more and more sugar. So temperature has typically an effect on solubility. If you raise the temperature, if the substance is a solid, more of it will dissolve. You'll notice that some substances aren't as affected though. If you look at salt, between 0 and 100 degrees, the change in solubility is maybe a gram for every 100 grams of water, 100 mils of water. So this will also help us to compare solubilities of things, see how much will dissolve, say maybe how much would precipitate, these kinds of things. And that's what we're going to look at. So solubility is how much we can dissolve in a certain amount of solution. The solubility curve shows us that degree, that amount that a solvent can dissolve a certain solute. The curves that we're looking at are all considered to be saturated solutions. So at any temperature, the point on that line or curve will be the maximum amount that is able to be dissolved in the amount of water given. Now, typically our graphs or tables are considered, or our units are in grams per 100 mils, not in liters. So what does that mean? Well, it's every 100 milliliters of water will dissolve a certain number of grams. This way it's easy, because we use 100 because it's easy to scale up, scale down, that kind of thing. Now, the other thing is you might notice people will say grams per 100 grams of water. It means the same thing. Remember that 1 gram of water is the same as 1 mil of water. So grams or mils, those units are you can switch them back and forth. It doesn't make a difference. So this is what a typical solubility curve looks like. And if you look at most of the lines on this graph, you'll actually see that most of them are moving in the upwards direction. So that means that as temperature is rising, so as we go this way on the graph, as the temperature gets higher, the solubility also gets higher. So we have this positive slope, meaning that solubility is increasing with temperature. Now there are a few that go down, and there's some special cases with that. You'll notice that HCl, KClO3 and SO2 are all, sorry, not KClO3, NH3, are all, the curves are all negative slopes. They're all going downwards. Well, that means temperature is still rising, but the solubility is dropping. So these things are actually becoming less and less soluble as temperature rises. Well, that indicates to us that those things are gases. Remember that gases are less soluble with high energy or high temperature, and solids are more soluble. If you think about what we're trying to do, if we want to get a solid, so we have this, let's say we have this chunk of solid, let's say this is sugar. And it's a bunch of sugar atoms, or molecules I should say, all stuck together. To get that to dissolve into water, we've got to separate out all those molecules. So we've got to put energy, I'm going to use NRG for energy, we've got to put energy into the sugar to cause it to break off into its separate molecules. Same with salt, NaCl. We've got to bust it up into Na pluses and Cl minuses. That's going to take energy, so energy's got to go in. But if you have something like CO2 that's a gas, it's already kind of spread out, it's moving quickly. If you want to get this to go into some water, let's say, into a liquid, we've got to actually form bonds, because the CO2 is not going to want to be stuck in that liquid. It's moving quickly, it's got very weak forces. We've got to actually form bonds, and that means that the energy, when bonds are formed, remember energy comes out. So that means it has to be cooler. So if you think about our heat of solution that we talked about before, breaking bonds takes energy, so you have to put energy in, and making bonds makes energy, so we have to take energy out. So here's kind of a summary of everything I just went over. So the curve shows us the grams of solute dissolved that would be in a saturated solution, so dissolved in a saturated solution that has 100 mils of water. And it shows us that all at different temperatures. Now, any amount below that line would indicate that a solution is unsaturated. So, if you're able to dissolve 80 grams and you've only got 60 grams, that means you have more room for solute to dissolve. Any amount above the line would be, if it's dissolved, would be supersaturated. I'm going to add that on, if dissolved. Because it might not dissolve. If you put more than it can hold, it might just sink to the bottom. Now, supersaturated is a special scenario where you can actually add more than you're supposed to. Put more, like let's say sugar. You dissolve more sugar than it's supposed to hold by heating it up. You get the extra to dissolve, and then you cool it down really gently. You don't look at it, you don't talk about it, you don't even touch it, you don't do anything with it, and if it sits gently enough, it will cool down, and you've actually tricked the water to hold extra. It's actually holding more. It's very unstable. If you drop a crystal of sugar in there, it will all precipitate, well, not all, the extra will precipitate out. If you bump it, even if you look at it funny, it will precipitate out. So it's a very unstable situation, but it can happen. Certain solutions will supersaturate. Now, if you have an amount above the line, but it's not dissolved, the excess, the amount above, so let's say you could only dissolve 80 grams, but there's 100 grams in there, and it's not all dissolved, well, then you would have 20 grams sitting at the bottom. So that would be the maximum amount. 80 is the maximum, and anything above would have to settle out. And it's the same with supersaturated. If you bump that solution, that extra 20 grams would have to come out of the solution. It's not allowed to be in there. Again, like I said earlier, solutes whose curves move upwards, in other words, their solubility increases with temperature. Those would be solids. Any curves who move downward would be typically gases because their solubility decreases. It gets worse as the temperature rises or goes higher. All right, so the easiest way to look at this is just to do some example problems. Now, before we do, I'm going to just go back to my graph. I'm just going to use the graph in the lesson here. And I'm going to just erase all of my notes, as many as I can, so that we can see the graph a little bit better. Now, in your work package, you should have a solubility curve, and that's the one we'll use for the worksheets. But just since this one's in the notes, I'm going to refer back to this one just because it's handy. The curves should all be fairly similar, but they are the numbers might be just slightly different. So we'll use the same curve. If we're all using the same curve, then we're all going to get similar values. All right, so the first one, we're just looking at what is the concentration. Another way to ask this question is, what is the solubility at 80 degrees Celsius of salt, KCl3, and KCl? So I'm going to flip back to my graph, and we're going to look at those three compounds at 80 degrees Celsius. So here's 80 degrees Celsius. We'll start with NaCl. So if I go up to NaCl at 80, I'm looking at just under 40, just under 40 grams per 100 grams of water. So maybe I'll just write 39 grams per 100 grams of H2O. I'm just going to write that there for now. Okay, so now we're going to look at KClO3. So at 80 degrees, I move my pen up to hit the KClO3 line, and I'm looking at, that's close to like 44. I'm just going to write the number for now, and then we'll write the answers on the other part. And then KCl, so I go all the way up to KCl, and I'm looking at that, and it's like 51, 52. Let's say 51. So I got 51, 44, and 39. So I'm going to go back to the question. Just one second. I'm going to copy those numbers down. 51, 44, 39. Okay, so going back to the question. So the solubility of these things at 80 degrees, NaCl would be 39 grams per 100 grams of H2O. Notice we say per 100 grams. Okay? We always want to include that because if we have more water, we should be able to dissolve more salt. KClO3 was approximately 44 grams per 100 grams of H2O. And then KCl was approximately 51 grams per 100 grams of H2O. Okay, that's all we need to do for that question. It's just asking you to read the values off the table. Now, if we're looking at this question, it's asking if we have KCl that's saturated at 0, how much more could 1 liter, so this is going to be important, hold at 50? Well, we'll deal with the volume after, but let's just look at KCl at 0 degrees Celsius and at 50 degrees degrees Celsius. So I'm going to flip back to the graph and we'll figure out how much we're able to dissolve at those two temperatures for KCl. So here's our graph. So KCl at 0 degrees Celsius, so I'm going to go up to here, that's about 27. And then at 50 degrees Celsius, KCl, I'm saying about 42. Okay? So if we're at 0 degrees, we can dissolve 27. If we're at 42 degrees, we can dissolve, 0 degrees we can dissolve 27. At 50 degrees, we can dissolve 42 grams. So we can dissolve more between those two temperatures. So let's figure out how much difference that is. So let's go back to our question. So at 0, we can dissolve 80, wrong value, 27 per 100 grams of water. And at 50, you can dissolve 42 grams per 100 grams of water. Now the problem here is we're looking at 1 liter. Now what I would do is I would say, well, how much more is it from here to here? And then we'll worry about the liter after. You could do it now. We could figure out how many grams that would be in a liter for each of these, but I'm going to shave off a step by doing it this way. So between these two things, 42 grams minus 27 grams will be 15 grams more per 100 grams of H2O. Now, we want to know how much more per liter, because that's what the question's asking. So now I know that 100 grams to make a liter, it's 10 times more, so it should be 10 times more mass. But not always will the numbers be so nice. So if we're able to add 15 grams more for every 100 grams of H2O, let's find out how much that would be in 1,000 grams of H2O. Because remember, 1 liter is 1,000 milliliters. So when I do the math here, basically the 1,000 comes up and multiplies by my 15, and I end up with x equals 15 times 1,000 divided by 100. Basically, I'm timesing by 10, so we can dissolve, 150 grams more per liter. So 1 liter would be able to hold 150 grams more. You could also have gone back and said, well, 27 grams in 100 would be 270 grams in 1,000. You can do that ratio here. And same thing here, this would be 420 grams per 1,000. And then take the difference, it would still be 150 grams. So I would just do it this way, at least right now, because that kind of makes sense. And to me, it's one less calculation. Okay, so that's the second type of question. So we're comparing 2 different temperatures, and also we had a different volume in there. Now, the next one says, find the amount of sodium nitrate needed to saturate 60 mils of water at 10. So we're going to have to deal with the 60 mil thing in a minute, but let's start off with our 10 degrees Celsius. So at 10 degrees Celsius, let's find out how much NaNO3 we are able to dissolve. So I'm going to flip back to the graph, and we're going to look up at NaNO3 at 10 degrees Celsius. So we'll use green for this one, and I'm looking at NaNO3 at 10 degrees Celsius. To me, it's right about there. And that looks to me like it's right on 80 grams. So I'm going to flip back. We have 80 grams. Where's my, there we go. So we can dissolve 80 grams in 100 grams of H2O. Now, we want to know how much that would be in 60 grams of H2O. So what we're going to do, it's going to be proportion, right? If you got 80 out of 100 on a test, well, if we reduce the test marks to a number out of 60, well, it would just be proportionately less. It still should be 80% though. So it's going to be out of 60 grams of H2O. Let's figure out how much that would be. 80 out of 100 would be something out of 60. So what you're going to do is multiply, like if you think of your math, you times both sides by 60 grams of H2O, 60 grams of H2O, and these will cancel, and we'll end up with our x value. So x is 80 times 60 over 100, and I'll use my calculator here. So it'd be 48 grams per 60 grams of H2O. That's it. The next one, we're looking at NaNO3, and it's dropping in temperature from 15 to 0. So again, same thing. And it didn't talk about any different volume, so we can just work in 100 mils. But from 15 Celsius to 0 Celsius, let's see how much we'll have to leave the solution. That's what precipitate means. It turns to solid, comes out of the solution. So we're going to look at our graph again here. And we are going to look at NaNO3 at 15 degrees and at 0 degrees. So 15 degrees Celsius, NaNO3. It's about here. I'm saying 84 grams-ish, 83, 84 grams. And at 0 degrees Celsius, NaNO3 hits about 70, I'm saying, let's say 73. So 84 and 73. Okay, so now we're going to go back to our question. So we said at 15 degrees Celsius, it was 84 grams per 100 grams of H2O. And at 0 degrees Celsius, it was 73 grams per 100 grams of H2O. So if we're at 15 and we can hold 84, so let's say it was saturated, we have it full. Now we drop the temperature down to 0 degrees Celsius. We can only hold 73. So how much has to come out? Well, it's the difference. 84 take away 73, 84 grams take away 73 grams would be 11 grams would have to precipitate. There's our final answer. Now, in your work package, there's going to be a solubility curve problems worksheet, and I would like you to try those questions using the graph that you have in your work package. That way then we're all using the same graph. It's maybe a little bit clearer than the one that's in the lesson. And kind of follow along and see if we can figure out these questions. We'll correct them together the next day.